All right, my AB kids, this is 2011 AB FRQ, Form A, number 5. We actually have done this in class before, but I think it's good practice for you guys. This is the one where I believe half the students that took the test this year got 0 points, or over half. I think you guys are in better shape than that. So at the beginning of 2010, a landfill contained 14,000 tons of solid waste. So we're going to write that down. And that's going to be T equals 0. And we're going to see that because T is measured years from the start of 2010. So that first sentence says when T is 0, the amount of waste is 1,400 tons of waste. Increasing function W. So we're going to write that down. W is increasing. And what does it represent? The total amount of solid waste in the landfill. So let me adjust a couple of things. So this one, let me move everything over. When T equals 0, W equals 14,000 tons. And I must say that W is the total amount of waste in the landfill, but we'll stop there. Then they give you this differential equation. That, again, you need to, when you see that, you have to think what it's really telling you. It's telling you the amount that the waste changes as time changes. So how fast the amount of waste is changing over time. And so here's our function about how fast the amount of waste changes. So we are going to read A, use the tangent line. Once you see tangent line for part A, the first thing you should do is the equation of a tangent line. Bam. And you realize you need a time. Okay, here's where, okay, let's look at this. I'm going to change this to a different color. Let's go darker blue or purple. Okay. W is our function. T is our variable. So in this case, our function would actually be a little bit different. Let me show you. Well, here, let me do this. So in essence, this is W minus W1, and this is T minus T1. So that's how you think about it. Now, you could leave that as Y's or W's. Well, technically, you shouldn't use W, because W is specifically reserved for the actual amount of waste. So if you were to use W, you're implying you're finding the actual function, in which we're not, so that would be very bad. So we need T1 and W1. So that's the actual time and amount of waste. Well, we know when T is 0, we have 1,400 tons. So we're done with that. So that part's easy. So in my equation, I can already do this. And now I just need to find the slope. But how do you find the slope of a tangent line? because this is a tangent line approximation, you should all know that the slope of the tangent line is the derivative. Well, we have the derivative. It's dw dt is the derivative, and we want to know that at the point where t equals 0. Well, in our function, we don't have t. We have w. But again, we know w is 1400 when t is 0. So that's just 1400. Now you don't have to simplify this, but it makes life a lot easier. So that will be 44. A way to think about this, shortcut, this is like $1,100 or $11. And this is a quarter. How many quarters are there in $11? Well, each dollar has 4 quarters, so 44. So that is our slope. So from that, we get that equation. That is the tangent line. And we want to approximate the amount of solid waste in a landfill. So we want to approximate W, which is the actual amount of solid waste, at 1/4. And it approximately equals, now this, if we solve for y, we get 1400 minus 44x. So that's going to be 1400 minus 44 times, where x is actually time. I could have actually put t instead of x there. I probably should have. Now we don't have a problem with a t here. Because t is just time. Now I had a problem with w because w was specifically that function, so that's why I didn't use it there. So t is probably more appropriate for time. There's our answer. We're done. This, you don't have to simplify any further. But if you choose to, which is unwise, you would get, is that plus? That should be plus. 1,411 tons. Does it ask for units? No. If you want to put tons, you may. So that's part A. So part B, this is a part that kind of confused some people. We have dw dt. And here's where you have to be careful. From that, we want the second derivative. And here is where I want to warn you. W is our function. T is our variable. Now, if we look at this, that is not our variable. So therefore, it's actually a function in a function. That is chain rule. That is actually box. So 1/25 is a constant. So when you take the derivative, the constant stays, and then you take the derivative of what's left. Well, derivative of 300 is 0, but the derivative of w, by definition, it is dw/dt. By definition, dw/dt is the derivative of w. So we're done with that, except now we read. They want in terms of w. We have dw/dt. So we need to replace dw/dt with what it is, and that's 1/25 w minus 300. So there is the second derivative in terms of w. Now, they want to know if it's under or overestimate our tangent line. This is part of your justifications. You should know this. A tangent line approximation, ooh, that is pretty brutal, is based on the shape. So if it's concave down, look, that tangent line's over. That tangent line is over. If it's concave up, that tangent line is under, and this tangent line, clearly the tangent line's under if it's concave up. So that's your logic. So we need to evaluate the second derivative. But if you look here, it's solely dependent upon w minus 300. If w is bigger than 300, then the second derivative is positive. Well, what is w? W is the amount of solid waste. Well, how do we know the amount of solid waste if it's bigger than 300, less than 300? So we have to take a couple of things here. It starts with 1,400 tons. Now, if you didn't have any other information, you don't know if that's always bigger than 300, because maybe they take some of that away or something happens to it. I don't know. You just can't assume that. But here's the next key thing. It's increasing. So if it starts at 1,400, it's increasing. It's always bigger than 1,400. So that's why we wrote this down. W is increasing, and it starts with 1,400. So you would say since W starts at 1,400 tons and is increasing, therefore W is always greater than 300. So d2w dt squared, the second derivative, is always positive. Well, that gives us a concave up situation. We know it's an under approximation. So now you would say the answer in part A, the approximation in part A is not and, is an under approximation. Why? Because d2w dt squared is positive on the interval from 0 to 1/4. 0 being our point of tangency, and 1/4 the point being approximated. Oh, that was part B. Wait, that all was part B. What are you doing, you wacko? Okay, so part B finished. We are done with that. Now I'm going to hide all this stuff and go to part C. Let me get my box and cover all this stuff up. Bam. So part C, particular solution. So a solution is something that you can plug in and it comes out to be true. So I need W. So when I plug that in, that statement becomes true. So let's do this. So normally, to find a function, if you start with the derivative, you would take the antiderivative. But here's the problem. W is our function, t is our variable. That is a function, not my variable. So whenever that happens, I can't just take the antiderivative when I have a function involved. So I need to do separation of variables. So I'm going to divide both sides by w minus 300. And we'll get the dt on the other side. So now we're able to integrate both sides. Let me erase all this stuff. Oh my, that's just weird. I'm going to integrate both sides. The right side's easy. That's a constant. It just becomes the constant times my variable plus a constant. That's my plus c. You don't need a plus c on both sides, because if you had on both sides, you would just combine them together to get one constant, so we're good. Now the right side, it is ln absolute w minus 300. So about that, be careful, because technically you're doing a u sub. You are letting u be w minus 300. So du is just dw. So replace that with that. Replace that with, that with u, and you would get this. Du over u, which is ln absolute u, plus c, which is ln u is w minus 300. So this time comes out nicely. But be careful, because sometimes it doesn't come out perfectly, because if you had a minus on the w, let me erase that. If that were minus, then you'd end up with a minus here, and it just changes everything. Or just be careful, because if you just do things out of habit, you can run into problems. Now, the next step, we're going to talk about a couple things here. We can argue that W is always bigger than 1200, the starting amount. So therefore, we could say this is always positive, so we don't need the absolute value. But we're just going to do it another way that works when you don't have those conditions. So to get rid of ln, I do e on both sides. Then we get absolute w minus 300. E to t over 25. Now I'm going to do something crazy here. E to the c. Now, this is equivalent to this, because you learned if you have exponents with the same base, you add the exponents. So it's t over 25 plus c. Well, that's what this is right here. So these are equivalent. Now, to get rid of absolute value, I put plus or minus. Now, if you put plus or minus 4 in here, it works. So that's what happens. So we're going to get rid of the absolute value sign and put a plus or minus. And I'm going to rearrange this. It doesn't matter, but it's prettier. So what I'm going to do, this is just a constant. E to this, E is a constant, C is a constant, plus or minus a constant. So I'm going to let K equal plus or minus e to the c. So I'm going to now rewrite this like this. Now I have to figure out that constant k. And we could have found c at this point, but it doesn't matter. We're going to find k now, and it's going to be pretty easy. because we are given initial conditions 0 and 1400. So off to the side, I will say when t is 0, w is 1400. This is just scratch, don't need that. So we're going to plug it in. 1400 minus 300 equals k e to the 0 over 25. That's just 1. So k is 1100. So I plug that in. Add 300 to both sides. And we are done. That is it. That's our final equation, separation of variables. Not too bad, but if you don't recognize separation of variables, this problem becomes bad because you get 0 if you don't recognize separation variables. That's it for number 5. Bye.